Hello everyone. So in this video I'm going to discuss about cross coverage in details. So in my previous video I have already covered the different types of cover points and beans, and generally what you will do in a normal cover group that you will just write a cover point, and each cover point will cover for a specific signal. So suppose in my design there are two signals, let's say logic A and logic B. So whenever I will write my cover group and uh, I will end it. So whenever I will write my cover group, what I will do, I will just write a cover point specifically for each of the signals. So that each cover point will focus for a particular signal. And if I just do this, it will just create the beans implicitly, and it depends whether you have what is the size of the signal and how many beans you have set using the set auto bean max. So you can also go ahead and just write implicit beans by doing this, and you can write much more. So in this scenario, each cover point will cover for only a single signal. But there might be some cases in which you want to cover a cross between multiple signals. That is, you want to focus and you want to create beans for multiple signals at the same time. So suppose you are dealing with a signal of RAM, and it has a signal that is write enable signal, and it has a input and it has a output. So of course, whenever the write enable signal is high, assuming that whenever it is high the write operation will occur, the RAM will be written with some kind of data, and we have to input that data using the input port. And whenever read write is low, that means it's a read operation, then you will get the data out of RAM using the output port Y. So in such scenario, we might want to perform a cover point that will not only cover a signal, it will cover multiple signals at the same time. So to do that, you just have to write cross, and then you have to mention both the signals or both the cover points. So in this way, you could just go ahead and perform coverage between multiple signals at the same time. So it is very important for lots of scenarios. So even in this, we are only concerned with the A signal whenever the read write enable is high, and we are only concerned with the Y signal whenever read write signal is low. So we can just go ahead and create various pattern and various cross between different signals. So this might be confusing, but let me just go ahead and write a very simple example of a RAM module, and that RAM will have a synchronous read and a synchronous write, and using that I will demonstrate the usage of coverage, of cross coverage. So let's go ahead and do this. So for my design I want it to be fully uh, parameterized, so I will just go ahead and mention the parameters. So my first parameter will be the width of the data, and for this example let's move on with 8 bits of data. And my second parameter just a second will be address width, and I want the address to be of let's go with 4 bits. So if address is of 4 bits, so the depth will be 2 to the power 4, which is 16. So there will be 16 locations inside this RAM. So let's move on with our main input signals and output signals. So first we have uh, the clock signal, and then we have another single bit signal which is write enable, and then we will have input signal uh, which is address, and since we have mentioned the parameter right here, we will use this parameter to determine the width of this signal. So I will just write ADR width -1 equals to 0. All right. So this the width of the address is of 4 bits, and let's move on to our other signals. So our another input will be the data from which you will feed the data to the RAM when the read write when the WR enable is high. And for that also I will use the parameter data width, and the signal will be data in. And our final signal, which is going to be the output for our module, will be the data out, and for that also the width will be same. So this concludes our port list. So let's go ahead and mention local parameters. So local parameters cannot be overridden during the module instantiation. So I want to declare the depth of the RAM, and so I will name that parameter RAM depth. Oh, and it will be of course it will be the 2 to the power the address width. So we'll just write it. So this signal, this module is fully parameterized. Now let's move on with our sequential logic. And before that, I will just declare the memory array. And for this, first, I will mention the data width. And then for the depth, I will mention it in the unpacked dimension. And in an unpacked array, as you already know that each elements are in separate memory location, and I want it to start from 0 so that it could just replicate an actual memory RAM hardware. But for the data width, since it is going to be some kind of data, I want the pattern that is that LSB is in the right side and MSB is in the left side. So this concludes our RAM array. So let's move on with the sequential logic. I will use the always FF block. And all right. So I want the clocking event to be the clock signal, of course. So I will just not write any label. So if read write if write enable is high, then the write operation will be performed. So I will just do that. So whatever is inside that data in, it will be returned to the address which is specified via the input. Else, if write enable is low, which means the read operation, it will just perform the read operation, which means data out will be given the value from the RAM. So this concludes the design of our RAM. Okay, before that, oh, I wrote a semicolon right here. And okay, there should be a semicolon right here. All right. And there should be a semicolon right here. So let's go ahead and check for any compilation error. Okay, the code is fine. So let's move on with our test bench. So I will write this test bench. Just a second. I will write this test bench as module test. And before that, I will include the ram.sv file so that every time I compile the test bench, the test.sv, the ram.sv also get compiled. So let's do that. So let's begin with mentioning our signals. So I will also include all the parameter inside this test module. So our first parameter was 4 and data width, and the second parameter was the address width, and oh wait, I think the data width, yeah, data width was 8, my bad, and the address width is 4. And then I will go ahead and mention all the signals. So our first signal is clock, and then write read enable or WR enable, and then we have another signals like address, and the input. And finally the output. So since we are not mentioning any directions here in the test bench, I will go ahead and mention the output in the same line because both of them have the same width. So let's go ahead and just mention the RAM module right here. So I will also mention the parameters. So to make it configurable using the test, I will just write these parameters right here. So I think our first parameter is data width, yeah. And second parameter is the address width. Okay, let's name our instance DUT, and let's do the wildcard port declaration. So I will first begin with the cover group name. So I will write the keyword cover group, and let's name this RAM underscore COV. And I want this cover group to be sampled at every clock. So I will put the clock as the event. And let's just put the posage of the clock. All right. So let's also name the instance of this cover group. So I will use the method, the option method name, and I will name it RAM underscore cover in capital letters. Now let's begin with our cover points. So for my first cover points, it will focus on uh, write the write enable signal. So I will name this write enable underscore CP, and I will mention the signals. So the beans will be generated implicitly, and let's move on with our other signal. So this will cover the address signal. So I will name it address underscore CP. All right. Now we will, I will mention a cover point for the data in signal. And for that particular signal, I will write some implicit beans, which will cover 3 different ranges. And those ranges will vary from low to high. So I will name the first bean low. And this will cover from 0 to the first third of the range. So first, let me just go ahead. I will just write all the beans. So the second one will be mid, the third one will be high. So the range will be divided into 3 parts, and that the first will be the low, the second one will be the mid, and the third one will be high. And I want this cover point, these cover point to be fully parameterized. So that's why I will use the parameters which are mentioned right here. So the first range will be from 0 to and the 1/3 of the depth. So let's go ahead and do this. So it will range from 0 to the depth. So I did not mention the local param for depth here. So I will just do that. Instead, I will just write a parameter. And this will be same to that right here. So I will just copy it and paste it. Oops. So this will range from 0 to the depth by 3. And then our second range will be from RAM depth by 3 plus 1 because it is already covering RAM depth by 3. So this will cover RAM depth by 3 plus 1 till uh, till 2 times or 2 by 3 of the RAM depth. So I will just write it. And similarly, our final one will cover 2 times RAM depth by 3 plus 1 to whatever is the final limit is. So I will just use the dollar. So it will reach till the final limit. So in this way, we have made our cover point to be fully parameterized. So let's move on and just write the cover point for the output. And since we will do the same thing for the output, that it is that we will just divide the ranges. So I will just go ahead and copy and paste this. So and this will be covering output and rest everything is same. So this concludes our normal uh, cover points for this coverage, and I will just go ahead and just create a object for this cover point. I will name the handle RC. So I will just go ahead and mention the clock signal. Since the clock is of logic data type, I will first instantiate its value to 0, and then I will forever toggle the clock. Let's say after every 5 time instance, clock will toggle. So this concludes our clock signals, and then we will go ahead and uh, do some we will provide some stimulus. So let's begin. So for uh, so I will just go ahead through every memory location inside the RAM. There are 16 possible locations, and it is because that the width of the address is 4. So I will just go ahead and I will write to every 16 possible locations, and I will write some random data. So in this way, we will be able to cover the all of the address locations, and also we will be able to cover all of the ranges of this cover point. So let's go ahead. And it should be less than the RAM depth. So in every clock cycle, I will just feed some random data. So I will use $u random range. And that range will be from 0 to RAM depth minus 1. Then I will just assign the iteration variable to the address signal so that it will iterate through every address from 0 to 16. And then I will set the write enable signal to high so that the write operation performs. And then I will give it a delay of 1 time slot, or I should say 1 tick of the clock, or 1 clock cycle. So using this, we can cover all of the possible locations in the RAM, and we will be writing some random value within this range to all of those locations. So we will do the same thing with the read operation. So for the read operation, I will just go ahead and copy this for loop, and it will just do the same thing, but instead of this, since we won't be writing any data, it is not required. And it will also iterate through every memory location, and this time the read write enable signal should be low, which indicates that it's a read operation, and then it will repeat with this delay. Or it should be group. Our group. And this should be AND group, right? Also, let's add a, a dollar stop right here. Otherwise, because of the forever toggling of clock, the simulation will keep going on. So let's open the QuestaSim and let's check whether our code is running fine. Okay. All right, let's run the coverage report. So we are getting 100% coverage, as you can see it right here. Uh, and here is our instance name, which we have mentioned using the option.name right here. And then we are getting hits for every beans. So for this particular for the right enable signal and for the address signal, beans are generated implicitly because we haven't mentioned any explicit beans. And for the rest of the signals, those are data in and the data out. There are three ranges, and each of the ranges are getting hits accordingly. So our coverage is 100%. So let's move on to cross coverage. So cross coverage will be a cross between two different cover points or signals. But a single cover point only covers or focus only on a single signal, as I have already mentioned earlier. So I will just quit the simulation. So to write a cross coverage, you instead of using a keyword cover point, you have to use a cover point. You have to use a keyword cross, and then you have to mention the cover points between which you want to perform cross. So I will label this cross. Let's say we want to perform the cross between the read enable signal, the write enable signal, and the address. So I will just write enable and address cross, and this will just perform the cross between these two cover points. So I will mention those cover points. So this is write enable cover point, and then just by writing comma, you could mention the other cover point. So just by doing this, it will perform a combination of every possible values uh, of the beans which are inside this. So since we haven't mentioned any beans here, the beans will be generated implicitly. So this right here will generate two beans because it is of single bit, and this is of 4 bit, so it will generate 16 beans. So there will be a combination between the first bean of this signal to each of the bean of this signal, then with the second bean of this signal to each of the beans of this signal. So let's just go ahead and just save the code and let's simulate the code. as you can see right here, that this cross coverage is mentioned as a cross, unlike the other things which are mentioned as cover point. So it's a coverage between uh, two cover points. So, okay. So as you can see that there is a coverage of the auto beans of each of or implicit beans of each of the signals, and we are getting 100% coverage, so it is getting covered. So since the beans are implicit, this might seem a bit confusing, and to counter that, I will just write explicit beans for each of the signals in just few little steps. So let's do it. So first I will mention the explicit beans for this signal, and what I will do, I will just write a bean, read write enable underscore b, which means beans, and I will use this empty array. I will not mention anything inside this range so that it will automatically infer the number of beans depending upon the range which will be mentioned right here. So, and I will mention the range from 0 uh, to the end of the signal. So I will do the same thing with that. So what it will do, it will just instead of writing auto bean 0 auto bean 1, it will just write wr enable bean, and it will make it easy for us to distinguish these beans from the beans of address. So I will do the same thing for the address signal, and for this also I will write like this and the same thing. All right, so let's simulate the code for one more time. Okay, the code is saved. Now it is more readable than before. So as you can see it right here that it is making every possible combination between the beans of two cover points. And those two cover points are for the write enable signal and for the address signal. So it is checking whether both of these signals uh, are asserted. Well, I mean, the beans are covered at the same time or not. So you can see it right here that first one is the when the write enable signal is high, and on the same time whether the cover point or whether the value of the address point is 15 or not. So it is checking for that. In a similar way, it is checking for 14, it is 15, and the write enable low, and etc. So this is how cross coverage works. So you can also mention explicit beans for cross coverage. So what is the significance of mentioning explicit beans for cross coverage and how can we do that? So let's find out. So right here, just like the regular explicit beans declaration, we would just mention this curly brackets, and inside this you could mention a bean. Let us suppose if I want to mention a bean which will only take hits when the uh, write enable signal is low. So is it possible to do that? Let's find out. So I will mention a bean and I will write it as write enable low. So I will use the keyword beans off. So to do that, you have to mention the keyword beans off, and inside the bracket, you have to mention the cover point for which beans you are interested at. So I am interested at the cover point write enable CP. So I will mention that right here. And then I will write intersect, and inside the curly brackets, I will write 0. So this basically means that I want an explicit bean which will only account for the hits when the uh, write enable signal or this cover point signal is low, and it will account for the combinations, all the combinations in which write enable is low, and whatever the value of address signal is. So this will create a explicit beans, and that bean will have all of these possible combinations. So let me demonstrate this. So here you can see that in this particular bean, the write enable signal is low, and here the value of address cover point is 15. So it will cover this particular bean, and it will also cover this particular bean because here also the write enable signal is low, and it will also cover this particular signal. So every particular combinations in which the write enable signal is low, it will be made or turned into a single bean. And so what about the remaining combinations in which the write enable signal is high? So it will not affect those signals in any way. This will remain as a separate beans. So let me just go ahead and just run the code instead of making it more confusing. So I will save the code. So let's run this. Okay, I made some mistake. Let's find out. All right. Mhm. Oh, my bad. I forgot to mention the keyword beans right here. All right. This time it should work. Yep, it got compiled. Now let's wait for the simulation. Okay, let's run the coverage report in details. All right. So what I will do, I will just open the transcript so that it can be zoomed. So yeah. So as you can see it right here that a separate bean has been created and it just left all the combinations in which the write enable signal was high, as you can see it right here. So in our earlier case, let's move on to our earlier case first. I didn't mention any explicit beans. So there were total of I think 32 beans. Yeah, 32 combinations. So each of the combinations created a separate beans, and each combination is carried out, and each accounted for a single hit. And you can see it right here that the, this is a combination when the write enable signal is high and the value of the address is 15. Then the second combination is in which the write, just a moment, in which the write enable signal is low and the value of the address is 15. And similarly, every combination was created. But mentioning explicit bean using this way in which I just uh, mention beans of keyword and I mentioned that particular cover point for which we wanted to create a separate explicit bean, and I write the intersect and 0, which basically means that a separate a separate bean will be created in this cross cover point. A separate bean is created, and this bean is taking hit for all the combinations in which the write enable signal is low, and it just left all the combination, as you can see it right here, all the combination, you can see every combination is 1. So it just left all the combinations in which the write enable signal is high. So still every combination is getting covered, and I mean it is what it is doing, it is just creating a collective bean of a single type of combination. So what is the usage of this? So it becomes really useful when you mention the keyword instead of mentioning beans. If you mention the word ignore beans, so this makes it a very useful thing. So what this will do, instead of making I mean it will still make a separate bean which will take all the values or all the combination in which write enable is low. But what it will do, it will not account or it will not count towards the total overall coverage. So this is a kind of filtering procedure, a filtering method. So the ignore beans just change the game. So using this, we could just collect all the values in which the write enable signal is low, and it will just account to a single bean, and that bean will be ignored. So if there are no hits for that bean, it will not affect the total cover group coverage in any way. So let's just go ahead and just save the code, and let's run the code for one more time. I've written the ignored beans right here, as you can see it, and let's do it. Oh, my bad. Hold on. So let's move on to our coverage report, which is generated during our latest simulation run. So as you can see it right here that all the combinations in which the right enable signal was low is turned into ignore bean, and it did get occurred 16 times, but it did not, or it will not affect the coverage in any way, and you still get the detailed coverage between the remaining combinations. So using the sort of mixture of the cross coverage, the ignore beans and the beans of an intersect keyword, you could just implement a sort of bean filtering mechanism in the cross coverage in an efficient way. So let's find out its practical usages. So first, let's create just let's quit this simulation. Okay, and let's go ahead and just create another cover point. That cover point will be very similar. So what this cover point was doing, that it is filtering out any combinations in which the right enable signal is low. So for the preceding combination, what I will do, I will filter out any combinations in which the right enable signal is high. So I will name this, let's name this something different. Let's name this one. And for this time, uh, it should be high. And we just have to change the value inside the intersect to be 1. So it will just filter out or make every B combinations in which the right enable signal is high as ignored beans. So this will do that. So let's go ahead and run the simulation. So let's move on to our transcript. And so as you can see it right here that we have created another cover point, which is right enable address cross 1, which is mentioned right here. And here, instead of like our previous cover point, instead of mentioning all the combinations or under the ignore beans in which the right enable is low, we have mentioned all the combinations in which the right enable is high. And all the different combinations are considered towards the coverage in which the right enable signal is 0. So this is the opposite of our previous cross cover point. So let's move on to a bit practical usage. So for a RAM, for this particular design, so whenever the right enable signal is high, the right operation will happen. And whenever the write enable signal is low, the read operation is will be performed. So what happens that when the write enable signal is high, value will be fed into data in. So data out doesn't concern us, and whenever the whenever the read uh, the read operation is happening or the write enable signal is low, we are only concerned with the data out because we will be looking for the data which is coming out of the RAM. So in this way, we can also filter out the combination for our practical usage. So let's do it. So I will write a cover point. I will name it write enable high. So when the write enable is high, it's the write operation. And on that time, we will be only focusing in the input or the data in cross. So this will just perform cross between the cover points in which we are focusing on the write enable signal and the data in signal. So I will write those cover points right here. And the data in cover point. Now I will go ahead and mention the explicit beans. So of course I will ignore those beans because I want to filter them out. So here I will name my bean. So I will name it write enable high. Oh no, I want to ignore all the combinations with write enable low. So I will name it write enable low. So all the combinations in which the write enable signal is low will be ignored. So I will basically write the same thing. So I will just copy it and paste it. So this particular cross coverage focuses towards the write operation, in which it will focus whenever the write enable signal is equals to 1 and whatever the value of the input data is. Similarly, we will create for the read operation, in which our focus will be that the write enable signal will be low and whatever the value of the output data is. So I will name it write enable low data out cross, and it will just perform the cross between the cover point of the uh, write enable signal and the data out signal. So I will ignore all the combinations in which the write enable is high. I will mention the cover point for the write enable signal inside this. So all the values in which the write enable is 1 will be ignored. So using the cross coverage and the filtering mechanism, we could just create some essential coverages of interest, which are very important to our design. So I will just save the code. and I will go ahead and run the simulation. Okay, it might be just a typo at line number 52. Yeah, now this should work. Yep. Okay, let's shift to VS Code for better readability. So, okay, this was our last cover point, and you can see it right here that the first cover point is for the write operation, and here it only focused on all the combinations in which the write enable signal is high, and it covered all the ranges which are mentioned as a beans inside the data in signal, and it ignored all the combinations in which the write enable signal is low. Similarly, for our read operation, uh, it focused on all the combinations. You can see it in which the write enable signal is low, and it covered all the ranges for the data out, and it ignored all the combinations in which the write enable signal is high. So using this method, we could just create combinations and create, I mean, we can also filter out certain beans or certain values which are undesired for our cross coverage case. So that's all about cross coverage for a very simple synchronous read and synchronous write RAM design. I hope you find this video useful and stay tuned for more. Thank you so much.